For some reason, I lost my. Give me one second only. I lost my. There we go. Okay, share screen. For some reason, I lost my. Give me one second only. Why I can't see the camera anymore?
We can see you on your screen if you're worried.
Yeah. I was playing with something. It's not important. Yeah, okay, we can start whenever you want. Just let me know.
I'll let them in. Okay, here they come.
All right. Good afternoon, everyone. Welcome to the High Performance Parallel R section week, if you wish, of this virtual summer training program that we are having this year. My name is Marcelo Ponce. I work at SciNet, which is the supercomputer center at the University of Toronto. With me today, we have also Eric Spence and Alexei Fedosev, who are going to be helping with questions in the chat. We have also Rancis Banson, who is monitoring all the activities and let you guys in, doing the recording of this section and everything. So if you are here, it's probably because you are interested in high performance and in R in particular. So without further ado, let's going to see what is the plan for today. And by the way, this is a new modality for us. If you guys have heard of us or know us, you know that every summer we run a whole week of different training events. But this year, because of the unprecedented situations, we are doing this in a virtual environment. So we would like, it's a different way of communicating. So we will really like to see and to know if you do have questions or anything, please write that in the chat. I'm going to try to stop once in a while and check my chat and see if there are any questions. Also, the guys are going to be looking at the chat. So feel free to put there any concerns, any questions, any comments. We would like to have it as interactive as possible given the current setup. So before starting, some details about the course and things that you probably want to be aware of. So this course, this 3 days course is, you can get credit for it, and the credit goes towards certificate programs. But for doing that, you will have to do a couple of things. You need to basically be here for 2 out of the 3 sessions. If you are here the three days, that's the best for everyone. But at least you have to be here for 2 out of the 3 sessions. Now, how we are going to test that is by taking an attendance test. And the attendance test is just to enter a particular code. I think the guys already posted in the chat the attendance code for today is 1. I show you how to actually do this. But the other important information, or the other important part for getting the full credit for the course, is that you need to submit an assignment, which I will try to present by the end of today. All the materials, all the slides are going to be posted in the course website, which is listed in the slides. But let me go there. So this is our course website. You see here on the right the description of the code, the Zoom meeting information, which you probably have already, otherwise you won't be here, the login information for accessing the Teach cluster, and this is the assignment that we're going to be talking today after. But what you want to do is to go to test, and then, well, I'm saying something different than you, but basically you will click on here, take attendance test, begin, and then you just enter the option. And again, for today, option is number 1. Okay, so you click on 1, you click on submit, and that's it basically. Okay. So that's the third order of business. That's the third thing you guys would like to do for today. Let me know, let us know if you have any questions or any problems with that in the chat again. Okay, also if you have questions, I think you guys can raise your hands. I will try again to keep a look at the chat and all the indicators in the meeting. All right. So first thing that, let's go back to the slides. What else? I think I mentioned all of this. Oh yes, a big thank you and acknowledgement to in particular Dr. A. Spence, who this material that I will be presenting today is based on. Also our previous colleague, Dr. Jonathan Darcy, was a main developer in this material. So all the credit goes to them. So what are we going to be talking about today and the next 2 days? So we're going to be talking about high performance or performance related issues to R. For doing so, we're going to discuss memory management. And if you are avid users of R, you know that R can be a little bit of a, a hogger of memory. Out of core computation, that's something interesting. Profiling, which is something that we need to do to understand how are we using the resources, the computational resources. Compiling code, this part is already in the material. I'm not sure I'm going to cover at first step this. Probably what will happen, just for the sake of the time, I'm going to push this, even when it's in the first part of the material, I'm going to put this at the end. So probably on Friday, we can discuss this. Then we're going to review a particular package called Parallel and the different implementations. So MC Parallel, Collect, and Apply are part of this package. So we're going to deep into that. And then other packages like for each and do parallel, and some more advanced packages, RDS for distributed shared memory, and PBDR, which is implementation of programming big data. So that's the big plan for today. It's a lot of material, almost 90 slides or so. So we will see how it goes. We will basically moderate the pace depending on your questions and concerns. And if you guys want to do actual hands-on, you can do it later. That all depends on what you guys prefer. Okay, any questions so far? All right, so first thing we're going to do, and let me see if we can do this together, because either if you decide to do it today or later, this is the crucial part, how to connect to the cluster and how to do things on a parallel environment. So let me see. So these are the instructions that you need to follow for doing so. So I'm going to log out. So basically what you need is a terminal. So if you're in a Mac, you just open a terminal. If you're in a Linux machine, you are just ready to go, probably pop up a terminal. If you are in a Windows machine, what I would recommend you to use is something like MobaXterm, which is a good option for connecting to the cluster. PATI is another one. Either way, you probably need one of those for connecting to the cluster. We have a third option, which I'm not sure I'm going to discuss unless you guys ask me to do so, which is to use the Jupyter Hub. So Signet has a Jupyter Hub that you guys can use. But as I say, unless there is someone interested, please let me know in the chat. And otherwise, I will just follow whatever is here. Okay. In the meanwhile, so what you had to do is basically open this terminal and now connect to the cluster. And for doing so, what you will do is SSH, which is the secure shell connection command, your username, and I'm showing here the Signet guest username at teach.signet.utoronto.ca. The -x is for getting some graphics back in case that we have it, but we're not going to use it this time. So let's try that. So I'm doing that on my terminal here on the right. Let me know if the font is too small or something. I'm going to go back to full screen with the slides. It's just to show you what I want you to do. And so what will happen usually is I have my key set up. So it's not asking for a password, but that will ask you for your password. And the situation may be that you're using your own Compute Canada or Signet account, then you have your own username, or you're using one of the temp accounts that we assign you. If you remember the course website on the right, there is this login information, and that's where you get the information for connecting to the cluster. Okay, so that's the first order of business. Please try to connect to the cluster. After you are in the cluster, you will see that it will say something like username at teacher1. Teacher1 is the login node for the teach cluster. And then we're going to go to our Scratch directory. Okay. And then we're going to issue this command, cp for copy, -r for recursively. So bring everything that is in there. And then we're going to navigate into the folder signed course. And that should say SS 2020, not 20. Oh, yeah, 2020. That's right. 9, which is the 9th event of the virtual summer school, HPCR, and then parallel R. Okay. And then dot for saying, okay, I want to copy all this here in this directory. So if you do that, it may take a second or two. Okay. And you should end up maybe more than a second or two, maybe like a minute or two, I would say. You should end up with a new directory called parallel R, where there are 3 subdirectories there: code, data, PVD, and setup. Okay. Any questions about this? If anyone runs into trouble or was not able to follow this, please let me know. Okay, I'm going to assume that everything is okay. We have 40 something people. So again, if someone is in trouble, please write something in the chat, raise your hand. I don't see any hands up. But hopefully everyone is in and copying the directories. Okay, after we have done that, what we are going to do is, yeah, it takes, that's true. Alisa is saying it takes a while to copy, and that's true because I can tell you why. It's a big directory. It has a lot of things in there. Well, not a lot of things, but very big things, or relatively big things. In particular, in the data directory, there are some large data sets. And the idea for today is to try to basically get an example of what you are going to be dealing in real life when you are trying to chunk on big data. So Amin is telling that he cannot, well, the thing is, so it's 9 underscore, I don't know if that is clear in the slides, it's 9 underscore HPCR / parallel. Sure, that is a good point. Let me see. We'll have to exit my 2 window view. Let me see if I can do that. It's a good point. Thank you for raising that. Someone was mentioning you cannot see what I write. Is that better now? For I wanna. Perfect. So yes, so coming back to Amin, yes. So, and that's, thank you, Amin, for that. Don't copy and paste from the slides for 2 reasons mainly. Number 1, you get hidden characters because the PDF is sort of a binary format. So when you're copying things from PDF and then pasting in a terminal, which is text-based, you get changes, things change. So don't copy and paste code from the slides. And second, it's good practice that you actually try to type the things by yourself, okay? Right, so yeah, so you need to write the whole thing, signed courses. And if you are familiar with Linux environment, you can use the tab completion thing. So for instance, I'm going to repeat my previous command. What is it? Oh, right. So cp-r, and then I'm going to type sign it, and then I press tab, and it will show me all the options I have. So sign it, course, and then SS 2020. And then if I press 9 and then tab, it auto completes for me and then parallel R and tab and autocompletes for me. So it's not so bad to have to type this all the way through. All right. So I hope this will help with that. So we have the data, and as you guys were noticing, it takes some time because it's almost 5 gigabytes of data. So there are some big files there that we will be working with. So the second thing I want you to do now is to use this command, the backshop. Okay. So if you type the backshop and now hit enter, what will happen is, and I just had to warn you, today the scheduler, which is the program in charge of giving you access to the different resources of the cluster, is not feeling too well. So we may need to bear with him or her. I not actually know the gender of this program, about some slowness and maybe unresponsiveness. Either way, what happens is when we use this debug show, what we are actually asking is to get one node where we can run our exercises. Okay. Otherwise, remember we were all connecting to the same login node. So it looks like someone is having trouble connecting to teach one. Kila, remember you had to write the whole thing, right? teach.signet.utoronto.ca with your username before. So yes, all recordings and live stream will be available. So yeah, so the recordings are going to be posted in the same course website, and actually this is open, so you don't even need to log in to see the recordings, right? So one thing to notice now, I'm in what is called Teach 36. So this is one of the nodes of the Teach cluster. I'm not more in Teacher 1, which is the login node, okay? So what I want you to do now is to use this command cd scratch again. So we're going into the scratch directory and now cd into the parallel R subdirectory that we just copied. Now, if you do ll there, you will see there are 3 subdirectories, then a setup file. And what I want you to do is to what we call source the setup file. And what it's going to do is going to load some modules, some software that we are going to be using. In particular, if you do ML, it's showing you, okay, we have an environment, a compiler, and then R. And in this particular case, we're going to be using R351. But that is all what the setup file is doing, okay? So now, without any further ado, you can launch R and you are able to use R in the cluster, all right? And follow along with the example. So this is the setup, basically. And it has some things that you have to do, but that's the way that you usually work in the cluster. If you're not too familiar with this, I will invite you to revisit the material covered in our first week, Introduction to Supercomputing by Ramses. And as I was saying, all the material is recorded and openly available in the education website. Okay. I think I didn't miss any questions. I think Ramses took the last one. Yeah, no, right. So let's go back to the slides now. And let us know if you guys are having any trouble with these steps. These are the mandatory steps in order for you to actually follow along with the rest of the material. I'm not going to be doing interactively unless that you guys ask for any of the examples, because it will take us the whole week and not just 1.45 hours per day. And so let me start by talking a little bit about high performance and R. So this course assumes that you know some R. All right, so I'm going to go fast on some things with R, but again, if you have questions, please feel free to write in the chat. Just a quick reminder, R is what we call an interpreted language. And because of this, there is what we usually refer as an additional layer of infrastructure, meaning that there is another program, it's an actual program, the prompt of R, waiting for you to input the commands. And then it's interpreted by this interpreter, obviously, and executed according to what the command requests to do. Because of this, interpreted languages such as R, Python, Bash, C are what we call not high performance because they are slow. So truly high performance languages, you may wonder, are things like C, C++, Fortran even. That being said, there are some things you can do to mitigate this slowness response, or not only mitigate the slowness, but also scale up to use multiple cores or multiple resources. And this is what we're going to be discussing today in this week, actually. So just a quick, very briefly review high performance computing. There are different motivations why you may need high performance computing. And one of the typical ones I would say is now you need to deal with large data sets. And examples can come from different fields, genomic, for instance, any kind of biology that deals with large data surveys, astronomy, although it's weird to find astronomers doing computations, but large data sets are very common nowadays. So one approach that people can take in this context is what is called the divide and conquer approach, which is basically you divide your task, the amount of work you have to do, in a smaller task, and then you distribute to workers. Let me use the word workers, in this case, different processing units, if you wish. And then each processing unit can work on that, making the workload a little bit more efficient. So the basic is how we split the problem into pieces, how we execute these pieces in parallel, and then how we bring back the results from these pieces. Well, the question is, okay, how we move this picture into R? Well, the thing is there are several packages that can help with this. And we're going to see some of them. Multicore and DoMC are a few examples. For multi-node, what it means is now we have, let's say we have resources like in the teach cluster that has more than one computer. Let's call it computer. Usually the proper name is node. Then you have other packages that do that. And this is the menu for this week, the packages that we can use for doing that. Now, before jumping into that, let me talk about something else, the different type of limitations that you can be facing when you have big data or big computations. So usually we classify in these 3 or 4 big categories. One is when your problem is memory bound. That means that the limiting factor in your program is the memory. So you're running out of memory, your program crashes or is swapping a lot. So that's something really bad. Second one is compute bound. So that is when you are actually doing a lot of computations, and if you have more things that can compute for you, that will benefit you. The third one is communication bound. So now think about dividing the work into different workers, and then what dominates is the communication between these workers for transferring the data. And finally, kind of related to the previous one, but independent as well, is when you have large data sets that are stored in not very efficient data format or file formats, and that dominate your program. So it's a file IO bound or dominated program. We're not going to be talking much about that, but there are ways to help you with that as well. Okay, and there is a limited amount of time that we have, so we need to pick what we want to discuss here. So let's start by talking about the memory-bound programs and R and memory utilization. So one of the things that you may know or not about R is that R passed by values. The values being passed are being modified. And what it means passing by value is that instead of doing a copy of the memory of the variable in memory, it just uses a pointer to the variable and modifies the variable itself. If R knows, because the function or program that is using does not modify the variable, then it creates a copy. And that can be dangerous because then you can fill your memory very quickly, especially if you are doing or dealing with large data frames or large vectors. So for mitigating that, R has something called garbage collection. So a garbage collection mechanism is a program that runs, again, it's another extra layer in the infrastructure of R, looking at variables that are not being accessed anymore. So when that happens, then the garbage collector say, okay, this variable is safe to remove from the memory pool. Let's clean a little bit the memory, let's release some memory. You can also force a garbage collector to work, but usually garbage collection theory is something that is very well understood and very well optimized. So usually you can rely on the garbage collector, although what we can do is we can use the garbage collector mechanism for keeping an eye on the memory footprint, meaning how much memory are we using. So what I'm listing here is some of the commands that allow you to use for memory management. So GC is the garbage collector command. You can use verbose equal true or just gc true. So basically, we'll give information about what is in the memory. ls is another useful command. It just lists all the system variables and functions defined in your current environment. Object size is another useful one to know how much space, what is the size of a particular variable. And rm is another useful one that allows you to basically purge, remove one variable from the memory. So this is a one-liner, what we call just one line of code that gives you something interesting. So in this case, I'm combining the sort command, the sapply command, any of the pi family functions commands in R are super useful. And then the ls with a function defined what is called inline, getting the object size of a particular variable and decreasing equal true, which is an argument for sort. So what this line is going to do is going to list all the variables defined in memory in a decreasing order. Okay, so sort, what happened here, applies to the list that or the vector that is returned by sapply, and ls, sapply will take all the elements provided by ls. Okay, so just one line here to play, you can try that. So for instance, in this case, and if you try to do this in your new R session, the cluster will be empty. So here I had a previously established section where I run my garbage collector. The garbage collector differentiates between vectorized cells and non-vectorized cells. So this is a different way on which R separates the objects that defines. And it's telling you how much is used, what garbage collector or what amount triggers the garbage collector and the maximum use, okay? So what I'm doing here is putting in this variable all mem the first two columns, because I'm interested on that, in use and megabytes, which is the representation of the bytes in megabytes of these quantities. So I'm storing that in all mem, and I'm creating a dummy vector full of zeros with a very large size, and then putting what is the object size there. So in this case, the object size is this large number in bytes. One nice thing is, because R is very object oriented, you can actually say, okay, give me this same value and specify the units. That's very neat actually. And so this is roughly 2 gigabytes of data, or 2048 megabytes. And now I'm going to collect what is the new memory use. And so same as before with all mem, garbage collector of the first two columns, and then subtract them. Because these are kind of stored as data frames, the subtraction goes very well. And you can see that basically the creation of this new vector X is the responsible for increasing the 2 gigabytes footprint in the memory. Okay, so nothing surprising there, just to show you a little bit of gymnastics of how you can keep an eye on your memory utilization. Okay, and as I said, this is a vectorized case because it's a vector, so it's kind of straightforward to understand what is going on here. Okay, any questions about this? Okay. So now let's say I want to clean a little bit. I use this vector as an example, and I can use it as a temporary allocation for computing something. So now I'm going to remove this vector. So we're seeing the rm command, and I'm going to recompute the memory utilization. So final mem is, again, the actual state of the garbage collector information, and I'm going to subtract final mem from all mem, and now I'm going back to 0. Okay, so basically, again, when you are using temporary arrays or vectors that are large enough, you may want to keep an eye in cleaning them, especially if you are at the borderline of utilizing a good amount of memory. If that vector is a temporary one, it's very likely the garbage collector will pick it up and clean it for yourself, but you don't know where. So at what state of the program will do that. So it's better that if you are not going to use it to clean a large vector, for instance. Okay. Any questions about memory utilization? So with that in mind, let's look at a package that specializes in helping you. Amin is asking, would it also be helpful to clear attached libraries this way? I would say so, because usually when you load the libraries, there is a small, well, it depends on the library, right? Some libraries are heavier than others, but take the example of, I don't know, plotly or ggplot. Those are kind of libraries that load a lot of things. So yes, in that case, I would say so. And that's why also R doesn't load all the libraries by default, right? It's in a need basis, if you wish. You load the libraries that you really need to use, otherwise you don't load it. And there is always a price that you pay for doing that. So if the library is too big, if and you are really looking at the micromanagement of the memory utilization, then probably yes. I will be more concerned with data structures per se, data frames, vectors, that with library. Usually libraries load functions. There are libraries that also load data, but usually it's more about functions. And functions, unless it's something really complicated, don't necessarily waste or use a lot of memory. But if you are starving for memory resources, that's something that you may be considering. Yes, that's right. And talking about memory, this is a package that will help you mitigating a little bit the issue of that you have a physical and unlimited and finite amount of memory, and that your data may be way longer than that. This goes also by the name of out-of-core computation, because it's related to how you put data in memory, but also do the computation. So what we're going to be talking about is a package called Big Memory. And what it does, Big Memory, is defines a generalization of a class matrix. And again, this is the object-oriented aspect of R. What it does is it basically, instead of loading the huge matrix in memory, because you may not have enough, it just load kind of a pointer, an index. It's called a file back object. So it breaks the memory, the matrix in chunks, and it goes and reads from the file where the matrix is defined, where the data is defined, and read whatever piece is needed. Of course, there is no free lunch here. You pay the price a little bit in performance, because now we are moving. Remember this classification we talked at the beginning of what part of the program is bound. We are moving the memory bound to the file IO bound part, right? So there will be much more communication and some processing as well here, but allow you to overcome the limitation of not having enough memory in your hardware. Okay, so this package is used a lot. It's used in other packages called Larger, Big Analytics, Big Tabulate, PVD. One of the packages that we are going to see at the end of this week also uses this package. So for looking at this, we're going to play with one of the data sets. And again, I'm not going to do it interactively unless someone asks for or is running into trouble. But please, before I start typing, bear with me a second, okay? So this is located in ideal gas data. It's a large data set of simulated data for an ideal gas where you have the pressure, volume, number of moles, and temperature. And you can load this. This is the small data. It's a CSV file. And you will see the data. So it's the raw name, pressure in pascals, volume in cubic meters, moles, and temperature. Now, the large data set contains 124 million rows. So this is roughly 5 gigabytes of data, okay? So the question is how we deal with that. Nowadays, this may be not so big data set, but I start to think that you create an ensemble of this configuration and want to compute energies and other states. So this can basically fill your memory very quickly. So first of all, do not run this. This is just an example of how you will create this backing file I was talking about, this mapping file, if you wish, between the actual data and the data that you will be loading in app. Don't run this, because if you run this, you're going to basically overwrite the file that is in the directory ready for you, and that will take several minutes. But this is how you will do it the first time, okay? You load the big memory package, and then you do read.bigmatrix, and then you specify what is your data source, okay? So in this case, is ideal gas fixed T large CSV. A couple of options, header false in this case, there is no header. A backing file, this is when you specify where you want to create this backing file. And just to notice, this is going to be a binary file, okay? And then a descriptor file is going to be a text file, but again, it's something that you need to create. So you will issue this command when you want to create this backing file, right? Now, let's go to the terminal for a second. Let's see my terminal. I'm going to exit R. So I'm here, I'm going to go into data and ideal gas. And you will see here the different files that we have for you. So we have the ideal gas binary file. So this is the one that is 4.7, almost 5 gigabytes. The descriptor file, and then a small CSV file. So these are the three important ones. This is the original one that was used to create the file, and now it's empty because you don't need that anymore. Otherwise, it will be even more space used here. Okay, but I show you how you will create it if you need to do with your own data. Okay. One thing related to that, and I'm not talking about this right now, is about file formats, right? This data could have been stored in a binary file format since the beginning, like a raw binary from R or HTFI or NetCDF, and that will help as well. But let's take the assumption that we are just dealing with big data and how we deal with that in this case. Well, this will be a way, okay? Now, assuming that we have created this backing file, which is already available for you in the directory, how we load it? Okay, well, we are going to load library with memory, and this is an option that you can use. If you don't want to get too much verbose response from the package, you can say quiet equals true. I'm going to see how much memory is going to use this thing actually. So I'm going to get my garbage collector for the first two rows as columns as we did before. And I'm going to load my data. How we do that? Attach .big matrix and then the name of the descriptor file. Okay, not the original data file, not the binary file, the descriptor file. Now I'm going to compute the new memory utilization. And you can see it's almost nothing. Remember, this data set weighs 4.7 gigabytes of RAM. By looking at the previous time stamp or memory utilization and the new one, you can see there is not much increase in that. Probably a little bit related to some things that the package has to keep in mind, the package itself, but not much more than that. Okay, so that's a little bit surprising. Now let's try to access the data because there's no 4.7 gigabytes of data in my memory. Where is that data? So if I do data 1, 2, then I'm accessing the first two rows of the data frame. I can try to say, okay, let's compute what is the minimum of the pressure in the data set. And for that, I will have to go through the 124 million rows of the data frame. So I'm going to compute min of P, being the minimum of the data in the pressure column. And I'm going to use this command that we're going to talk in a little bit. It's called system time. It basically measures how long it's taking that command to run. It's a way to profile, and that is our next topic in the lecture today. It's a way to profile how long does it take this command to execute. And it's separated in three categories: user time, system time, and elapsed time. You always want to look at the last time. It's the combination of the two previous ones. The user time is related to the actual command. The system time is related to things like the operating system time to access some files. And in this case, because we know all the data is not in memory, R and the operating system work together to access the data. So the total time is, in this case, 11 seconds. If you run it, it's probably going to be a little bit faster because I did this timings long time ago. Actually, Eric did this timings long time ago, and probably this part is not up to date with the actual numbers, but you will see something that is palatable. It's not so bad. Okay. Yes. For P, that's a great question. Some of the packages I'm going to be calling today are part of the R basic image, and some are not. Big memory is one of the ones you need to install. Okay, and it's very straightforward. One thing I should warn you though, don't do this while you're in the debug shop. So if you have to do this, open a new terminal, connect to the teach cluster, do the setup, and then do R install package big memory. Okay, you can try in your own laptop as well if you want. So big memory is not one of the complicated packages that may fail. But yeah, you need to install that. Thank you, Key, for that reminder. So we compute the minimum. We have the minimum is 90,000 pascals. And if I look at the memory footprint, it still remains barely empty, I would say. So this command, which basically scans through the whole column, didn't need to load the whole data in memory. But it takes a considerable amount of time. It's not just milliseconds as you will spend nowadays, but it's taking some time. Okay. Just a summary of in-memory is a package that can help you if you are starving for memory resources. As I mentioned before, there is a price to pay. Some of the price will be related to file input-output operations, which are usually very, very slow compared to any other computation, or just handling the data itself. Okay, and you need to accommodate the data to fit in the big memory picture, this descriptor and backing file that we talk about. All right. Any questions about this? And Q, let me know if you run into any trouble or anyone else runs into any trouble installing the R package big memory. All right. If not, I'm going to move to the next topic, which I was telling you just a second ago, is about measuring things, about profiling. As the technical name that we give to when we want to measure by different kind of metrics, how a program performs, how fast it is, how much memory is using, how much data is dumping. So as you can see, I already mentioned 3 different metrics, 3 different things to quantify. Yes, Q, that problem that you are seeing, so Q is having a, hello? Okay. Yeah, you can speak, I'm fine with that. Sorry, I having some interference, probably it's not coming from here. Anyway, so I hope that you guys can hear me okay. I'm having some noise in my transmission, but that's probably just me. If you guys are hearing something weird, please do let me know. Is everything okay with the sound? Okay, thank you. So, perfect, thank you guys. So the problem that Q was reporting, let me make a short quick. So this is what is going to happen. If I try to install packages, big memory, for instance, here, it's telling me, look at the first message that you get from R. It's telling me, okay, because you're in a shared environment, I cannot write in the home, in the bare installation, the base installation. So I'm going to put things in your home directory. Now, one thing that happens is when you're in a debug shop or you're running things in the cluster, your home directory is read-only, so you cannot write there, all right? So for mitigating that, what you need to do is you open another terminal. I'm doing that, my computer is a little bit slow now. Okay, let me open a new tab here. Okay, I'm going to SSH into teach again. .ca. Okay, going to go to Scratch and then the parallel directory just to source. Going to source again the setup. Okay, so my modules are loaded. I'm going to launch R. Notice that I'm in teacher 1 now, right? Teacher 1. Going to launch R there. Do install packages big memory. Big memory. And now it's no more complaining about the read-only thing. Okay, the error you were getting was because, and now I select just the cloud directory, and now the error you were getting is probably because you were just trying to do that in the debug shop. Okay, now it will take some time to compile because it does some things and link with other libraries, but try that. 2 terminals open. One, I'm going to cancel this. One with your debug, with your debug shop running one of the nodes, and the other running on the login node on teacher one. Okay, makes sense? Try that and let me know how it goes. Okay. In the meanwhile, and anyone else who wants to try that, because as I say, big memory has to be installed. In the meanwhile, let's talk about profile. And somehow, when we look at the beginning, the garbage collector command is a way to profile memory utilization, what we call the footprint of the memory of the program. We're going to look at different options here, more related to performing, to profiling the performance of the code related to how much time it takes to run. So for doing that, we're going to use micro benchmark and then the system time. We saw system time just a second ago for computing how long it took to run the minimum in the pressure, and then rprof, which is an R profiler, as you can imagine. So let's look at some examples. I'm going to define a very dummy function that does nothing, basically. Just iterate in a loop a million times, adding one to a variable, doing nothing, basically spinning wheels, and just demonstrate how to use system time. We saw that before. System time, of this case, the function gives you the user. The system, notice that because this is not using any file or anything, it's very tiny, and then the elapsed amount of time. Okay. Now, this is very crude, very raw, and in some cases it's useful because it just gives you an idea. But a way better approach is to use this library micro benchmark. And every micro benchmark is already, well, you probably need to install micro benchmark, but I think it was already part of the R installation. If not, you probably will need to do the installation, but just give a try. So what is different with micro benchmark? How does it work differently from system file? Well, you do micro benchmark of the same function. The call is very similar. Instead of doing system time, you do micro benchmark. But the nice thing of micro benchmark is that it runs many times the function itself. So it can give you a more appropriate measure of the actual time that the function takes to run. So it will give you the minimum, the mean value, and the maximum. So you can get a dispersion, a distribution of how long it takes to run. Okay. So it tells you what is running, minimum, mean or medium value, and maximum, and the units, milliseconds in this case. Okay, the other was seconds. So very interesting library to take into consideration. I'm going to show you another example. In this case, a function called admit, which basically add two vectors or two variables. So this is the polymorphism of R. You can use vector or variables in this case, and just return that. And then a test function that basically iterates a million times using the admit function. And why I'm doing this is just to show you how we can basically report and measure different functions being called by other functions. So for doing this, we are going to use rprof, the R profiler. This one is for sure, is part of the R basic package. You don't even need to load a particular library, just use rprof. The way it works is similar to the sync command. I don't know if you have used sync, but basically you initialize, you start the profiler, and you give a file name where to store the data. So rprof, and in this case, rprof data, it could be examples data, something like that. And then I'm calling my function test, which is this function here, which runs a million times, calling the admit function. And then you stop the profiling by doing rprof null. That way, the profiling of whatever is being executed stops. For analyzing what was the output of rprofiler, you do summary rprof, and you load the same data file where you basically dumped all the profiling of what you wanted to do. So in this case, I'm putting this NS. One thing that is useful sometimes to look at is what columns, this is going to be a data frame, what columns are defining this summary profiler. In this case, we have by self, by total, sample interval, and sample time. So these are the different quantities that rprof will be looking at. So I can do S by total, which is a useful way to look at. So you will see which part took the longer. So for instance, test, which is the main function here, took 100%. And of course, because everything was running under test. But it also tells you the self time or the self percentage. Admit, which was the function being called by test, took 62%, 62 percent, I saying right, of the total time. The total time was 0.82, the actual percentage was 62%. But the operations themselves, the addition to 5% roughly, or 4.5, and then the creation of this, and we're going to talk about this at the end with iterators, the slicing of the vector from 1 to a million took 3% of the time. So you had a way more digest view of where the time was being used, the actual time, the percent time, the self time, and the self percentage, meaning from the total time, what percentage took. Okay, so this rprof is another way to profile. It's very useful for profiling whole programs, because now you just have a script, and this will be part of your assignment. You have a script and you can throw the rprof at the beginning, rprof at the end, and then do the summary to see where most of the time had been used. Okay, super useful, highly recommended tool to use when you want to know where you are spending most of the time. And this is important, right? Because if you have a program that takes too long to run, you may want to know where you need to focus your attention to improve the performance. You don't want to be spending the focus or the work that you want to do to improve the performance in a part that is using a meaningless amount of time in the whole program. So the first step to improving performance is to look and see where the most expensive parts of your code are. Okay, I hope this makes sense. Okay, so a quick summary of rprof. The rprof samples are taken every 20 milliseconds by default. You can change that. You start rprof with a file name and you stop it with rprof null. You can read the file using summary rprof. Results are given in data frame, which is nice to deal with, and then the different columns that you have in the data frame. Okay. One very parallel comment I'm going to do here. In a sense, we have seen two different ways of profiling here. This is called sampling. The profiling that rprof does is a sample. Basically, every X amount of time goes and look at what instruction is being executed in the program. But if you use system time recurrently in your code, that is what we call a tracing approach. So you instrument the code to see how expensive each of the instructions in the code are or take. Okay. Any questions about the profiling part? Okay, I will take that as a no. And this is the part where I was going to talk about compile code. But as I told you, I'm going to jump ahead. We're going to keep this part for the end, for Friday if we have time, because this is a way to also improve the performance of your code. We talk about R being an interpreted language, but also is this extra infrastructure, but also you can put some compile language there. So Milena is asking about what units is rprof. I believe it's rseconds. Okay, I believe in this case we are talking about, let me see, I believe these are seconds. I had to double check that, but I believe these are seconds. Okay. And I think you can specify that as well. No problem. So let's skip ahead. So there's a lot of things, good things here in the compiled version. I hope we will have time to talk about that on Friday. Sorry, on Thursday. Our last class is on Thursday. But let's jump ahead and talk about scalable data analysis. And that's probably the core part here, because are the libraries that will help us to do parallel jobs or run things in parallel, meaning concurrently doing different things, several things at the same time. So once you turn into parallel computing, there are two problems you need to solve. My program is too slow, and then perhaps using more resources, processors will make things go faster. This happens when usually, if you go back to this classification with the beginning, your problem is what we call compute bound. And then the tools that you can use, that we're going to discuss, are parallel or multi-core, and then this RDSM, which stands for R Data Shared Memory. The other problem you may be facing is my program crashed due to lack of memory. So somehow we try to mitigate this with the big memory package, sorry. But there is another approach, because the problem with the big memory is that if it is really big data, you will move your problem from being memory bound to file IO bound, and that's not good neither for different reasons. But maybe we can still apply this divide and conquer approach we talked about before. So we can maybe divide into smaller pieces, send these to different workers that has their independent memory pool, and then collect the information. So in this case, we are talking a memory bound problem, and the tools that we can use are as well parallel, Snow, and you will see multi-core and Snow are actually part of the parallel package, and PBDR, which again, I hope we can talk about this on Thursday. There are many other things that can be affecting and most related to this IO input-output operation bound things, and different things you can do to approach this problem. I'm not going to be talking about these ones today, but let me know if you're interested. We can have a discussion about this any other of these days. I'm trying to focus more on the material that you will need for the assignment, and also the material focused on improving computation. Okay, so that's where we are going here. So how we use multiple processors in R. So this is what we're trying to do now. So there are many packages that can help with this. Parallel is a good one. Include two other packages, multi-core and Snow. So let me tell you about multi-core. It allows you to use different cores on a computer. So a thing that we should clarify here is, maybe I should bring, let me bring our documentation about the teach cluster. Sorry. There we go. So I'm going to be, we're using the teach cluster, but something similar happens with our main cluster. So what happens is, in the cluster, you will have a device, a hardware device, more or less like this. This is what we call a node. In this node, there are actually 8 processors, 8 CPUs. And this is something very common. Nowadays, even your phone, your mobile phone has 8 CPUs. Your laptop has 4 or 6 or 2 or 8, depending on how beefy your laptop is, CPUs. So when I'm talking about cores here, when I say multi-core allows you to use all cores on a computer, I'm talking about the CPUs. How many cores is a synonym of CPUs you can use in the same hardware. Snow, on the other case, not only allows you to use all the cores on a computer, but also across different computers, or what we call nodes in the cluster. There are other packages that we're going to talk about. For each, it's a different interface, but a similar functionality. RDSM is a shared memory parallelism. It works with big matrix, the one that we talked before, and PDBDR is a very hardcore implementation, which similar scope to Snow. Okay, so I hope that we will have time to talk about all of them. We're going to start by talking a little bit about system parallelism, and that is because R, in the way that is compiled, in the way that is installed in your computers, in particular in a cluster like ours, has already some parallelism, intrinsic parallelism. And what does it mean? It means that when you do this kind of operation, so for instance, we define a matrix, big matrix in this case, and then we do some kind of matrix multiplication. That's the operator for running matrix multiplication. And you look at the utilization. So this is a command I'm going to show you in a second, that you can see how much utilization is in the CPU. When it shows something that is bigger than 100%, it means that it's using more than one just core. And that is what is happening here. That operation that was utilized or performed here, the matrix multiplication, because a really big matrix, then it's using more, that is using more than just one single core. Okay, and this is something that comes already implemented in R, the way that R performs mathematical operations, in particular when we are dealing with vectors or doing slicing or doing anything related to the apply family functions. So that's why they are so convenient to use. Okay, so let me show you this example, or not necessarily this example, but how you will do it. Let me touch my screen here. So I'm going to have my two terminals. So that's the one where I did installation. So look, I'm in teacher one. So this is the login node, right? But my debug shop, which is running in the other terminal here, is running on teach 36, right? Actually can take a peek. There's no one else here. So I'm going to launch R here. I'm going to create the matrix. Matrix A. It's going to take our norm, and I'm going to use a million elements or something like that. Okay, and I'm going to create another matrix B. And so I have now two big matrices in memory. Oops. About that. So you can see they're using a meaningless amount of memory. So, but what I'm going to do here, I'm going to connect to the same node where I'm running R, in this case, teach 36. Okay, if I do who, okay, that's something that doesn't matter. So I'm going to use, there are two things you can do there. You can use the top command, which basically tells you whatever is running on that computer, how much resources and memory is using. And I'm going to do A times P, okay? At the same time, keep an eye. So if I can shrink this, I can show you in real time, keep an eye on the utilization. So in doing that, what did I like? So I have my matrices. Oh, okay, I think I forget to specify the number of rows. My example again, what do they have for number of row? Oh, I see. Okay. So let's do something else. 6 and row is going to be even bigger, the matrix. Okay, we're running out of memory here, so I will need to shrink a little bit this matrix. Not too much, because I still want to get something meaningful. Okay, as you can see, it's taking a bit longer. And you can see R is using 100% now, right? That's because it's creating this matrix. Okay, a little bit longer than expected. See. Okay, maybe we should try to do something smaller. So this is the kind of things, real-time kind of troubles that you can run when you are starving for memory or resources. All right, maybe it's not worth spending the time in this part, but you can try to convince yourself if the things come back to me, which doesn't look like, we can try this again. Okay, the idea is here that you will be seeing this thing utilizing several CPUs. There was another command I wanted to show you. I really like this command a lot. It's called htop. Htop's give you an idea. Look at this. So now we're using, so this is a look of all the cores in the node. It's very graphical, very similar to top, but it also gives you this information about the utilization. And one thing that you may not notice is, I have another colleague here, one of the designers, I guess, Fox trying here. One of the things you may not notice is the memory is not so bad, but because the node is shared across or along several of us, then we have a fixed amount of memory for each of us. So that's why I'm running into trouble here. One thing I'm going to do is I'm going to kill this R process. So I'm going to kill myself. Well, not myself, but the R process. So I stop it. I'm going to launch it again. Let me see if I can try with a smaller matrix now. this way. N times N equal N. It still is too much for that. Anyway, you can try that. It wasn't expected to take too long. This may be also related. We can still take a peek at what this is doing. I think this is memory related. It could be also related to certain other things. Oh, there we go. Now let's do the multiplication with A itself. It shouldn't be as bad as in the example because we have two options of similar size. But let's see how it goes here. Still not seeing. So I've seen 100%, but no more utilization. This again may be related to the way R was compiled. But in general, you should see some parallelism, intrinsic parallelism already happening. Okay. No, that's right. That's right. Thank you, Francis, for reminding me about that. So you only get one core. That's right. So that you all, although will get hyperthreading. Anyway, so Rancy has a very good point. I'm actually going to cancel this. I have this disclaimer in the assignment, indeed, that you need to use -n to get more than one core. By default, with the backshop, you get only one core, and that's why I'm limited to this 100%, and I won't be able to see that unless, again, I'm going to kill this process. I'm going to exit my debug shop, and as Francis was saying, the backshop -n4 should give me 4 cores. Okay, I don't want to get stuck on this for too much. I'm now on teacher 2. I'm sorry about that. But you can try that. Okay, it's an interesting exercise to do, but I just don't want to spend much more time. Sorry about that. Okay. Any questions about this? In any case, that's something you get for free without any much that you had to do. Okay. Now let's talk about explicit parallelism. That's what we are going to get with the packages. And I should mention that other packages also allow to have explicit parallelism. And this is an excellent review, what is called the high performance computing. What is the name? A name for. So R has a few teams looking at specialized things, and this is the one looking at high performance computing. It has a list of all the packages that you can use. Some are more specialized, some are more general, as the one we are going to be using today. They even have ones for GPUs, if you want to try that. Okay, it's an incomplete list, I would say, that I'm listing here. Now let's talk about the parallel package. That's where we are heading now. And the Parallels package since 2011 is part of the core R. So this one you don't need to install. It comes with R by default and include two previous packages, multi-core and Snow. And these ones were the ones we were talking at the beginning, the one that allow you to use multiple cores in one node or different processors across different nodes. Now, one other thing you should be aware, multi-core does not work on Windows machines because of the different operating system, just to make you aware about that, okay? How do they work? Okay, so multi-core uses something called forking. So what happens with forking is you have a main process running, and then it creates clones of the original process with replicas of the code, of the instructions, and the data itself, okay? And that is very, very convenient because you don't need to communicate the information to these child processes. They already get the information, they inherit the information from the main process, okay? Snow, on the other case, creates entirely new processes, and they don't inherit the data. They don't have the original data. So we need to send the data and then take it back, okay? Each approach has advantages and disadvantages. This utilizes a little bit more of memory and a little bit more of time for administrating and performing all this. This one is a little bit lean on that, but supposed to have less memory and less utilization footprint in the child processes. Okay, but if you need the data, you will need to grab it specifically. Okay, and this is called spawning versus forking. Now, let's look at the particular implementations. The simplest use of multicore is to use something called MC parallel and MC collect. MC parallel basically forks a task to run in a given function, and MC collect waits for this task to finish and collect the results. That's why they collect. So let's take an example. Let's use now the airlines data set. And we're going to focus for a particular month. So again, I'm going to warn you, this is going to be similar to your assignment. What we're going to do is we are going to tackle the airline data set for a particular airport. And I want you to generalize this approach to all the airports in the data set. So this is just to warm a little bit up. We're going to load the parallel package again with quiet equal true or not, that is up to you. I'm going to source this script that lives in the data airline, and it's called read airline, read underscore airline.javascript. Basically provides a function, read.airline, to read the data and basically massage a little bit the data, and we're going to see exactly what it does. So I'm going to read the January 2010 data from here, data airline R0T, ROT 2010-01, that's for January. I'm going to get now the unique planes, but I'm going to use MC parallel for that. So usually how you get the unique planes, well, look at the data itself. You can explore the data. There are different fields, but the one that we're interested in is the tail number. It's like the ID of the plane. So what I'm going to do is unique, sort, and then get the length. And I'm going to compute the median, for instance, of the actual time that took the flight. So again, NC parallel and the actual operation I want to do, median of elapsed times, and I'm going to use NA remove equal true because there are some NAs in the data, okay? This is real data collected by the IATA organization. And this is all good. It's like I plan ahead what I want to perform in parallel, and then I want my answer, which I need to invoke by using NC collect. And I want the answer that include both computations. So I want a list given by the unique planes and the median elapsed time. Okay, so then I do answer, and this is what I get back. And there are some decorations we need to discuss. So the first one, 30,113, corresponds to the process. This is the ID of the process being run in the computer, and this is the actual answer. Okay, 4,555 is the unique number of planes in this data set, and then 110 is the mean or the median actually elapsed time for the flights. Okay, and this is in minutes, and this is the process that took care of that computation, right? So it's very straightforward to implement, I would say. You have your data, you invoke with MC parallel the function or the task you want to do, and then you do MC collect to actually perform the action and recover the data. Okay, so you use these decorators and then things happen in parallel. Okay, another example of this is, let's say that we want to create a feed between the column, which is distance, and their time. Their time is the actual time that the plane was flying. The elapsed time is since people board until people landed and leave the plane. And in this case, I want to create a feed between the distance and their time, and then the arrival delay, the delay at the arrival, and the departure delay. So different type of delays. Okay, how I will do that? Well, this is serial. Huh? No parallelism of any kind. So I'm going to do system time, remember the profiling, and now I want to compare how things improve with respect to parallel implementations of the first feed. We're talking roughly about 1 second or so. And then the second feed to 0.52 seconds. In total, let's say 1.5 seconds both feeds. Okay, I just look at the looking at the lapse times. The user time here, I'm not considering kind of because it may be related to some other things. But we're talking about roughly 1.5 seconds. Okay, or 1.7 if you consider the user time. Now, how we will do this in parallel? Well, I'm going to define a function, parallel feeds, which runs the first feed, same exact case as before, but then I'm doing MC parallel. Second feed, again, MC parallel, and then MC collect of the parallel feeds. Okay? And then I run my function. And in this case, the system is 1.685 seconds. Okay, so there is no real advantage between doing the 1.7 something and 1.6 something. So what happened here is probably there wasn't enough data, even when the data set is not lean, there wasn't enough data to do this. And this is something that happens many times. The forking of the processes and the waiting for rejoining the data may take some time itself. And so we sometimes when we do parallelism and we see that, this is called overhead time. When we do that, when we see that, it means that there is not enough work to be done in this case. Maybe the algorithm, the feed, the linear feed was simple enough. So what we will expect in a productive case is that the actual time takes way longer than the overhead time. And then in that case, it's worth applying this type of parallelism. Okay, but as you could see, the parallelism itself, the explicit parallelism that we are imposing with the MC parallel and MC collect is quite simple. It doesn't require much modification to the code. It just include the MC parallel and MC collect. And because it's quite simple, it's also true that you won't see as much benefits and in more hand-taking care parallelism. Remember, this every time that forks a process is copying the data and the instructions. So that's why it's sometimes a little bit heavier and you don't see much benefit unless you have a really, really big task to perform. All right. How are we doing with time? Okay, 10 minutes to go. So let me see, because this is what I want you to actually implement in your assignment as well. What we are going to do now is a clusterization of the data. We're going to use a k-means approach. And we're going, as I was telling you before, we're going to just focus on the O'Hare Airport for this 2010 data, okay? So k-means is a very simple randomized method of picking different clusters. So we're going to try to see if there are ways we can aggregate this data and identify like clusters or clumps of data that they are connected somehow. So what we're going to do for that, notice that we're going to load our data file, in this case, the ORD, O'Hare delays, just for the Chicago airport in this case. And if you are interested in to know how to obtain this is what I did. You don't need to do this again, but you will need to do something like that for the total amount of data. So what I'm doing here is defining which are the columns associated to different delay measurements. I'm selecting the Chicago airport. So you don't want to do that in this particular case, but you don't want, but what you want is to pick the different delay columns. Okay, all the airports, but just the delay columns. Remember our ARM command from the beginning and clean a little bit the memory, so there is no mod memory footprint from the original data set. And then in this case, and this one you will have to do also, you will have to choose the delays that are positive. And then complete cases give you the rows that actually has complete data. There are a lot of NA, as I told you, this is real data, so it's real data is messy. So by using complete case, cleans the data a little bit, okay? Serial implementation of k-mean algorithm of clusterization with k-means. System time, putting in serial results, k-means, the original data frame, number of centers, number of neighbors to start by looking at. So these are parameters of the k-mean algorithm. We can talk about that if you want, but basically take this as given. And this is the time. It took roughly 1.3 seconds to run this. So nothing too heavy on the time utilization on the runtime of the algorithm. We can look at the results. In this case, the bituneness is another parameter that tells you how far apart the clusters are. Just a particular number, nothing too profound on this. Now, what I want to do is to run this multiple times. So as we saw, the original time wasn't too surprising, but if we run 14 random trials, is the same as running. So that was determined by this n start, 40 random trials. It's the same as trying 10 random trials 4 times. So we're going to try to do that using lapply. Again, applies are very efficient functions in R. So what I'm doing here is defining a function do nk means, and that's unique for using the apply functions. It calls the k-means on the data. I keep centers equal to 2, but then n star, which defines how many times you will try, is given by the argument end of the function. Now I'm going to time this by using the lapply function with repetitions of tens 4 times, and then calling my function do nk means. In this case, we are talking about 1.9 seconds, even a little bit longer than the serial version, okay, with the applied family functions. I can use sapply now to look at the different quantities returned by the result in the list results. And for instance, look at which one was the minimum in the case for the total withinness, which is another parameter of the k-means classification. And we get the results. Some people may tell, and that's true, we need to include this post-processing in the time, and that may take us to maybe 2 seconds or something. But it took a little bit longer, right? The problem here is the overhead from splitting up and starting the process 4 times. So even when the apply functions are very efficient, clearly in this case are cutting us short in improving the performance. So how we do this with MC apply? Well, or MC parallel. Well, MC has also MCL apply function. As you can imagine, it harvests the L apply functionalities, but in parallel way. So I'm going to do, instead of the L apply implementations, MCL apply. And it's basically the same plus an additional argument, MC cores, which tells in how many cores you want to run this. Okay, so I run this, I obtain my times. And again, this should help me a little bit better. It's not much meaningful. And again, it's because the data set is sliced. So what I hope is when you look at the whole data set, this will improve substantially with compared to the serial time. And I'm getting my results again. For doing that, I get from the list. We combine the results. I'm sorry, this should be res, not this res. Oh, no, sorry, that's fine. Res are here. So I simplify my applying from the function for getting the total withinness. And basically, I get my result for the betweenness, which is the same as we got originally. Okay, so this is the parallel implementation. We went through the serial implementation here to apply family function implementation, which in principle should be more efficient, but it's not because of overhead of breaking the data, to a parallel implementation using multiple cores. Okay, that's the hope. One thing that you can take a look at is, and again, this is a screenshot of something you should be able to do as well, is to see four different processes being run when you use these commands. Okay, and that you will do in the in a way as I was showing you before with 2 terminals, for instance. Okay, let me see how much time. I think we are roughly at the time, and this may be a good point to stop. There is a little bit of material that I would like to cover, and it's part of your assignment, but we can talk about this tomorrow at the very beginning. Let me show you, in the meanwhile, the assignment that I have for you guys. So this is posted in the course website as well. The idea here is, as I was showing you, to process the Chicago O'Hare Airport using the parallel package, I want you to follow, to refollow these steps, okay? So what I want you to do is, first of all, I want to create a script called parallel examples.r, including comments. This is very important. I want to be sure that you guys understand what you're doing, but basically following the example that we just did in class, okay? The example that we just went through, just follow that example. Then I want you to run this example using R command batch. If you haven't used this one, it's very useful because at the same time that run your example, it will generate a file called .rout containing all the commands and the outputs for that, okay? So that's the first part. Just go through the examples we discussed. It's very simple, I hope. Just go through the examples, put them in a script, run the script and generate this output file, okay? Now what I want you to do is to modify this script, create a new script called parallel examples all airports. Recall this is just for O'Hare, all airports, and implement the k-means clusterization for all the airports. As I told you at the beginning, you will, or not at the beginning, but just a few minutes ago, you need to clean the data, not slicing by airport, but just removing the delays that are not positive and the complete cases, selecting only the complete cases, okay? That's the first 4 parts. It looks like lengthy, but this is very verbose more than anything. This second part, we are going to be talking about tomorrow, the load balancing part. So either I can keep it out of the assignment, that's not very important. You know, the assignment is more an excuse for us to know that you are following along the material than anything else. But let's talk about this tomorrow. And hopefully I will be able to cover that in the first 15 minutes. And then I can tell you about other ideas that you can use to keep increasing the implementation of this assignment and make something useful and meaningful for you. Okay, Francis is reminding me about what is the due date of the assignment. I was hoping, because I believe the assignment is simple, it's just following the material alone. We can do it tomorrow midnight, Wednesday midnight. But if you guys are struggling with that, if you think that you need more time, I'm okay. I put a hard cut off of Sunday midnight. Okay, so in principle, it's going to be it can be even Thursday before the class on Friday, because it is I can show you what I will do for implementing this. But again, this is more excuse for you to show us that you understood the material and follow the material. No more than that, okay? So we can chat about the deadline tomorrow, but start by looking at this, just following along the examples, being able to reproduce the examples. That should be good enough, okay? Okay, so any questions? Otherwise, I'm probably going to stop the transmission now. Looks like there are not too many questions. Didn't see any hands raised. All right, so I think we can stop here now. One more thing I forgot to mention.